All right, let's get started. So just going to go over the test today, and I'm not going to give you specific answers. I'm just going to show you the methods, and I encourage you to try it because, again, I'm not interested in like just giving you answers. It's more like what's the approach because you're trying to learn this material. So the first question is you had a 115 kV line with a characteristic impedance of 44.1. Find the maximum load that can be supplied prior to injecting or receiving power. If you recall, when we did transmission lines, right? If we assumed a lossless transmission line, then our characteristic impedance is going to be square root of L over C. And then to find your power, remember it's V squared over R or X. This is just going to be V squared over X. So that's going to be V squared over my characteristic impedance. It's a lossless line, so it's purely inductive. So now the question is, which voltage do I need to use? Well, remember, a transmission line is a three-phase transmission line, which would be 3 times V phase squared over Z line, right? Well, V line is equal to the square root of 3 times V phase. So if I substitute V line in here, let's take a look and see. I have, well, let me put this V line divided by square root of 3 equals V phase, right? So if I've got 3 times V line over the square root of 3 squared, all that divided by ZL, that gives you your SIL. So these terms will cancel, and then you're left with your line voltage divided by Z sub C. And if you were below that, the load, the current through the line is going to be consuming VARs, but not enough to overcome what the Y over C values would be. Okay? If it's greater than that, now the current through the line is actually consuming more VARs than can be supplied by the capacitors, and now the line consumes VARs. So prior to that, the capacitors are enough to make it up. So it actually puts out VARs or supplies VARs. In the other case, it's consuming. Questions on that? All right, let's go to number 2. Well, it's not panning. Why aren't you panning? Okay, number 2. So number 2, you had a short transmission line with V phase is equal to 115 kV. I told you phase voltage. Remember, I said always assume line voltage unless you're told otherwise. This was equal to V phase. The line has a Z equal to J 151 and S per phase is 15 plus J 12 mega VA, right? So you could do this a bunch of different ways. You could certainly set up your ABCD parameters. VS, IS equals A, B, C, D times VR, IR, where A is equal to 1 because it's a short line. B is equal to Z. C is equal to 0. And D is equal to 1, right? Now the only thing you need to do, solve for VR. That's the phase voltage, right? So that's at an angle of 0. And IR, you get from S single phase divided by V phase, and you take the conjugate of that. You would get both VS and IS to solve that. A lot of all over the place type stuff with this one. People, kind of got lost in what the what the values would be and which ones to use. You just have to be careful to do that. Yes, sir. What? It's a short line. So C is equal to 0 in a short line. Smile, right? Yep. So C is equal to 0 in a short line. Any questions on number 2? B?
Why do IR over 3 times to be the
Because S is a single phase value. Why would I divide it by 3? If it was a 3-phase value, I'd have to divide it by 3, but not as a single phase. Right? And the problem description was specific. The load is blank per phase, not total. Any questions on number 2? This one I just really wanted to see if you could use the ABCD parameters and didn't have a lot of having you worry too much about square root of 3. But some people actually made it more complicated by putting 3s or square root of 3s in there. That wasn't what I was intending to do. Any questions on number 2? Okay, number 3. So you've got a Z and a Y. So I'm just going to go ahead and show what the parameters are. 1 plus ZY over 2. That is also equal to D, right? They're the same value. But these have the units of ohms. A bunch of people left them in ohms per kilometer. So to get Z and Y, you had to take the little z and multiply it by L, and the same thing here. A bunch of people forgot these were ohms per kilometer. My Z and Ys, my big Z's and big Ys, has to be actual ohms. So you have to multiply those by the length of the line. That is A. B was equal to Z. So that was the easy one. And then C is equal to Y times 1 plus ZY over 4. What's that?
Y times A.
Or Y times A, yep. Oh, no, not Y times A, because A is only 2, right?
Oh, yeah.
So then the process is exactly the same as the previous problem. VS, IS equals A, B, C, D, which you've just solved for, times VR and IR. So over here, the line is operated at 220 kV. So VR, and unless told otherwise, it's a line voltage. So you had to convert that to a phase voltage before you could solve for it. Now, IR, right? IR says it's 200 MVA at a 0.8 lagging power factor. That's 200 at an angle of inverse cosine of 0.8. And then I divide that by, if this is VR as a single phase voltage, then I had better put 3 times VR and take the conjugate of that. Questions on all that so far? Because the next page had us doing sending end power. And again, it depends. So if you left this here as a phase voltage, and I'll write one phase, you'd multiply V times I conjugate, but you had got to include the fact that there's a 3 in there, right? A lot of people forgot 3s or square root of 3s. But again, it's important that we include all those. And then my percent voltage regulation, that was V no load minus V full load over V full load times 100%. Do you all remember the equation that we did for A? We said A was equal to, let's see, VS. Oh, let me back up. It's VS. I want to make sure I have that correct. So A times VR is equal to VS when IR equals 0, right? Under no load conditions. And we solve for it that way. So isn't A by definition, or not by definition, but A or VR when IR equals 0, isn't that the definition of no load? VS divided by A is the VR at no load because IR equals 0. You can see that even in here, right? VS equals A times VR. And if IR is equal to 0, there's no component. So you can directly get the no load voltage just by dividing VS over A. So V no load is here, and then V full load is VR. A lot of people didn't include the voltage regulation equation, but a bunch of people were not even sure how to get the no load voltage. It's just VS over A, right? That's all it is. Questions on that? Because a lot of people got tripped on that one. A lot of people got tripped up on efficiency. Efficiency is purely a real number. Some people included magnitudes and angles. That's not efficiency, right? Power is just real power. There is no angle associated with it. That was it. Questions on problem 3. Yes, sir.
Is there a reason why it's not both on?
What? The length of the line was, what was the length of the line?
8 kilometers.
It's right at the limit. And since you had all the ABCD parameters, all the values to calculate, you remember what I said in class? I'm like, it's always better to be more accurate. So I would always just use the medium length lines if you can get them. So the short line is going to be close, so we can ignore it. But if I have the parameters, it really isn't that much more work to calculate it. So calculate all 4. Number 4, we started doing Newton-Raphson, right? And you had 2 functions. F1 equals x1 squared plus 3x1, x2 minus 4 is going to be equal to 0, right? Because we're doing root finding. And F2 is equal to x1, x2 minus 2x2 squared plus 5. That's going to be equal to 0. I have 2 variables I'm solving for. So that's my matrix of unknowns. I've got my 2 F equations. So my Jacobian, F1, F2, x1, and x2. So I need the partial of F1 with respect to x1, partial of F1 with respect to x2, partial of F2 with respect to x1, partial of F2 with respect to x2. And I just got that from the form of the Jacobian, right? I laid out my functions, and then I picked my variables, or put in my variables, and then it just kind of screamed at me what the Jacobian needed to be. So let's do the partial of F1 with respect to x1, 2x1 plus 3x1. Let's do F1 with respect to x2, 3x1. That's it. Now I'm going to do the partial of F2 with respect to x1, x2. Partial of F2 with respect to x2, x1 minus 4x2. And that's it. Yes, sir. Say that again, partial of f1 with respect to what? 3x2, yes, thank you. Yep. Now, step one. You were given x1 and x2 for your first guess. Check. F, and I'll put a matrix here, of 1, 2. Does that equal 0? It didn't. So then you had to go through and do one iteration. So your delta x is equal to the negative of your Jacobian, which is a matrix, evaluated at x1 equals 1 and x2 equals 2. Inverted, multiplied by, then you updated x1, x2, after one iteration is equal to x1, x2 for my 0 iteration, plus my delta x. And that's if you had to do one iteration. If you just ran MATLAB, MATLAB would build it in for you. Questions on this one? Say most people had a general idea how to do that. There were some people who didn't show me their work, so I couldn't give them credit. Remember, you can't use MATLAB to spit out the results. You've got to show me what you're getting. And so I tried to be very clear on that. Most people did, but some people just showed their equations, and just showed their results, and that's not sufficient. Number 5. Why do you always need a slack bus? You need a reference, and you can never know exactly the losses in your system. So that slack bus has to make up the difference for all the line losses. It's going to be able to put whatever P and Q in or out, or take it out, whatever P and Q is necessary to make sure all the system line losses are accounted for. So if you don't have that, you can never really run a load flow because your system is not going to work. You're going to have too many line losses based on the scheduled and demanded power, and you're not going to have basically KCL. So having a slack bus means KCL is going to be met. Always, always, always. Those were the two. And with that, that should have been an indication for problem number 6. Given a 10-bus system, what is the maximum equations that you can write? 18, right? If you have to have a slack bus, you can't write 20 equations. You got to write 18. And what's the minimum? Well, you got to have to write at least one equation, right? So if you had 9 slack buses plus 1 generator bus, you'd only have to write one equation. Unlikely in the real world to do so, but it's conceivable that that's what you'd have to do. So what I was looking for there was, do you understand enough about the Jacobian? Not the Jacobian, about the algorithm. Any questions on those two? Yes, sir. You can have a slack system. You can't have a system with entirely slack buses because you're not doing any load flow, right? You know all the magnitudes of the voltages, so you don't even do a load flow. You have to have at least one bus type that you don't know either the magnitude or the angle to even do a load flow. So that's what I'm saying. You need at least one generator bus. Otherwise, you're not doing a load flow. If you had at least one load bus, then you could write 2 equations, but like, what's the minimum? It's 1. Okay. Last problem. I'm not going to do Y bus because you're all pros of that. But remember, you have to invert, right? Those are given to you as Z's. Those aren't Y's. So a bunch of you all forgot to invert. First part. The second part. You had a system This is bus 1, 2, and 3, right? I told you this was 200 plus J100 and 200 plus J100. And I even told you that this voltage here, whoops, did I tell you that voltage? Sorry. I don't think I told you the voltage. Yeah, so. Well, based on what we did a couple problems ago, you know you have to have at least one slack bus, which is good because I don't know the real and reactive power demanded at that bus, right? Got no idea. I just know there's a generator connected to it, but I don't actually know what that generator is scheduled to produce for power. And it doesn't matter anyway, because I still need a slack bus. So I got to have one slack bus. I've got a P and a Q here and a P and a Q here, which means I can check my results for both P and Q at bus 3 and bus 2 to obtain what those values, if I'm getting the correct values. So what do I need to solve for? V2 and theta 2, V3 and theta 3. Those are the unknown variables. I don't have them specified, right? You could have said, well, maybe I make one of those a generator bus or make it as a slack bus, but I know I got to have at least one, and I know what the power P and Q is going to be, and I've got no generation connected to those, so I'm not going to take a chance. I'm just going to assume I have one slack bus, and the other two are load. And because I've got 4 unknowns, I had better write 4 power balance equations. At bus 2, I know the power demanded, so that means I can check there. Both real and reactive. And the same thing at bus 3. Those are the function names I need to solve. What equation do I determine theta? That's the name of the equation. It's the power balance equation at bus 2. Because if you remember from a generator bus, we know the voltage magnitude and the real power. We don't know the angle. So we solve for theta 2 by using our delta P2 equation. And then lastly, our Jacobian, right? Here are the, well, let me put it in order. So delta P2, delta P3, delta Q2, and delta Q3 are the rows. Here are, oops, the columns. And that tells you the form. So this would be delta P2 with respect to theta 2, and on and on and on and on. You didn't have to do a real Newton-Raphson load flow, did you? But you had to understand them to be able to pull off that last problem, right? Paul. No, I just needed to know delta P2. If you wrote out all 4, you didn't get credit. I needed to know which equation you need to write. And it's delta P2. Class average was an 84. I think you could get a possible 125 points, right? In the test. Everybody still okay with that? You earn your points. I don't give them to you. No, you're not okay with that? Would you rather just base it off 100? Because I can change the score to be whatever you got divided by 125, if that's what you prefer. But I would prefer to have you guys earn you folks earn your points. Not scale to a curve. But hopefully what you're seeing with this test, because again, Newton-Raphson is really tough to do an exam on, because it can take you, the entire exam time to do one problem. So I'm trying to do more concepts there. Do you understand the concepts? thoughts or comments or feedback?
Yes, I'm confused by what you were looking for on Charlie on 7. It's
I just wanted the function names to solve. I wanted
you
you
have 4 f of x's, p2, p3, q2, q3, and the x's are the thetas, theta 2.
These are the function names I needed. These are the f of x's that you're using to solve or to check to see if your unknown variables are actually at their correct values. So you need those 4 equations because you have 4 unknowns, right? 4 equations, 4 unknowns to be able to get the answer. Does that answer your question, Taylor? I think that was Taylor.
Yeah, that was me. We can talk offline. That's what I put down, so I was confused why I missed it. I wanted to make sure I wasn't missing something.
I'll have to take a look. Any other comments or questions? You happy, sad, in the middle? Glad to be more than halfway done with the material, right? Because all we have is one more exam and a final, and we're already done like 4 or 5 labs and 4 or 5 homeworks. Got about a month of classes left, 8 classes. All right, well, my present to you is I used to always cover new material because I was like, let's pound new material, but there's very little value added to cover new material now. So even though we've only been doing this for about half an hour, I will let you go early and we will pick it up on Thursday. Have a great day. I will see you all on Thursday. Take care, everyone.
Thank you, Paul.
Thank you.